Let's begin with the first factor. What atom is the charge on? Suppose, for example, we are comparing the following two acids to each other. An alcohol and an amine. So we've already said that in order to compare these two acids to each other, we have to draw out the conjugate base of each. The conjugate base of an alcohol is RO-, and the conjugate base of an amine is an amide ion. Now, in this case, the negative charge is on an oxygen atom, and in this case, the negative charge is on nitrogen. To compare these two to each other, let's take a closer look at the periodic table. We identify the location of oxygen and nitrogen on the periodic table, and we see that oxygen is right here and nitrogen is right there. So we are comparing two atoms in the same row of the periodic table. Whenever comparing two atoms in the same row of the periodic table, whether we're comparing nitrogen and oxygen, or whether we're comparing sulfur and chlorine, any two atoms that are in the same row, the operating trend is electronegativity. Electronegativity increases in this direction up to fluorine. Fluorine being the most electronegative. The noble gases are not particularly electronegative because they already have an octet of electrons. Fluorine being the most electronegative element. Oxygen less electronegative than fluorine. Nitrogen even less electronegative than oxygen. So if oxygen is more electronegative than nitrogen, it means that it can better stabilize a negative charge than nitrogen. And that means that between these two, the negative charge is more stable on oxygen than it is on nitrogen. And if the alkoxide ion is more stable than the amide ion, that means that an alcohol must be a stronger acid than an amine. This is the trend that we observe when we're comparing two elements in the same row of the periodic table. However, consider the following example. Imagine that we are comparing water and H2S. H2O and H2S. If we want to compare these two compounds to each other and say which one is more acidic, so we need to draw out the conjugate base of H2O and the conjugate base of H2S. So we need to compare these two to each other and say which of these conjugate bases is more stable. Here the negative charge is on an oxygen atom. Here the negative charge is on a sulfur atom. But notice this time when we identify the location of oxygen and sulfur on the periodic table, now the two elements are in the same column of the periodic table. Now, when we're comparing two atoms in the same column of the periodic table, the operating trend is actually not electronegativity. It is true that oxygen is more electronegative than sulfur. However, there is another principle that is operating here that is more dominant than electronegativity. If we compare the size of these two atoms, we see that oxygen is relatively small compared to the size of a sulfur atom. So if you have a negative charge on an oxygen atom versus a negative charge spread out over a larger volume of space in a sulfur atom, the negative charge will be more stable spread out over a larger volume of space than if the negative charge is concentrated on a small volume of space, even though oxygen is more electronegative than sulfur. See, when you're comparing two elements in the same row of the periodic table, for example, if you're comparing nitrogen and oxygen, so the difference in size between nitrogen and oxygen is fairly negligible. And therefore, the dominant effect, the dominant factor is electronegativity. Oxygen, more electronegative than nitrogen, can better stabilize a negative charge. O- more stable than N-. But when you're comparing O- and S-, electronegativity is no longer the dominant factor. The dominant factor is size. Sulfur, being so much larger than oxygen, is more capable of stabilizing the negative charge, and therefore SH minus is more stable than OH minus. And if SH minus is a more stable conjugate base than OH minus, therefore H2S must be a stronger acid than H2O. So what we've seen are essentially two trends. So in order to determine whether electronegativity or size is the dominant effect, you always have to look and see the two elements that you're comparing to each other, where are they relative to one another on the periodic table? Are they in the same row or are they in the same column?